All right, I'm just going to walk through some low-hanging fruit on this glider optimization. So I have in here the baseline glider. This really hasn't been optimized for much. You've been through a really basic design process, and I've walked you through each of those steps, but we really haven't optimized this very well. And there are two main things I guess I would see as really low-hanging fruit that you probably want to do at a minimum. And by the way, this is before I've corrected this for the spiral mode that this glider has an issue with. But again, we can correct that even after we've optimized it. So, okay, so let's just walk through this. So I've got my spreadsheet over here, which you're probably familiar with. This is just my design spreadsheet. This was my original design spreadsheet. It's got some extra stuff in it as I've played around with things. And so I made a copy of that. And I'm calling this Doug's Improved Glider. So this is just, again, the first step I would take in trying to optimize this. So over here on glider calculations, I'm just going to start walking through what I would do slightly differently here. So probably the biggest thing, the two big things that I'm going to attack here are one, the size of my ballast. So my ballast, that's that washer sitting there, and really for most aircraft, you're trying to remove weight. This thing will fly further if I can remove weight on the aircraft. And of course, we can remove weight by making the lifting surfaces smaller, but that's not nearly as effective as reducing the weight of this carbon rod, which I'm not even using this stuff up here. I mean, it is offsetting the CG a little bit by having this weight up here, but I could significantly, I could reduce the length of that, cut that back, decrease the drag and weight of this section here. I can also move this guy forward and make him smaller, so it's less weight, but I can still get the CG in the location that I need it by moving it forward and decreasing its size. I probably don't want to take away any of the lifting surfaces because what I'm trying to do is maximize L over D. I want this thing to be as efficient as possible. I'm going to need as much lifting surface as possible. So for this glider design, I don't really recommend removing or getting rid of the surface area that you have access to. Remember, we have 9 square feet of surface area. Of course, you can distribute that however you want to throughout these lifting surfaces, but so let's just start by the thing that I would start with here is this tungsten ballast. An easy way to reduce the weight of this ballast is just to move it forward. So I'm trying to get my center of gravity. Let's come back over here to my center of gravity. So I want the CG to be at minus 0.0569, and so I'm gonna see how far forward. If I left this whole carbon fiber rod on here, and I just shifted this forward, let's see how far forward I could come. Okay, so I've got to have it connected to it, so I'm just going to scooch it back here. Okay, so that's about as far forward as I can get with that guy. So let's see where that's at. So that's at a 2.6353. So I'm going to shift my tungsten ballast forward to 2.6353. And now that's going to move my CG location. So I can now change the outer diameter of this guy because I need my CG. Remember, if I come back here to my center of gravity, I need that to be at minus 0.056. I guess it's wrong in this particular thing. What I'm trying to get that to is minus 0.056. So now I'm just going to change the outer diameter of this thing. Of course, I could change the length of it. I can change either the length or the width, I guess, of this washer, or the outer diameter to whatever I want to, as long as it's greater than the 3/4 here, so it can slide on here. So after some fiddling around, it looks like about 0.0855. If I just shrink that diameter, that gives me back to that CG location pretty close. Okay, it's not exact, and I might need to iterate on that later in the design. But for now, I mean, other things I'm going to change are going to change the CG anyway. So this is kind of my best guess right now for the size of that. So that's an outer diameter of 0.0855. And I think this is going to ask for a radius, right, for this. So the radius, so half of 0.0855 is 0.0427. So this is what that looks like now, 0.0427. So I've just got a little tiny thing sitting out here. Like I said, I just moved this forward and decreased the weight. Now you can see the weight of the aircraft has now reduced because the weight of this particular thing, the tungsten ballast, dropped. Remember our weight, and right here is my weight in pounds. I don't have that labeled. This is weight in pounds force. It used to be 1.1 pounds. Now I'm down to 0.77. So, we dropped 30% of the weight of the aircraft there by just shifting that forward. So that was a big gain. Okay, so now let's come back over here to the glider calculations, and I have the weights here calculated for my main wing, horizontal, vertical, fuselage, ballast, and aircraft, and these are getting copied in from the previous tab over here. So this is my inertial calculator. I've got the masses here, and then I use those to tell me the weight. So again, the whole weight of my aircraft right now is 0.774. Okay, so that was one really low-hanging fruit, and I could now walk through this process again, and I would already be better off just by moving my CG forward. That reduced the total weight that this airplane has to carry, and therefore is also going to reduce the drag. We also did actually reduce the drag, and let's talk about that for just a second. Down here I've got these, like A14 is where I was computing the drag of the dowel and the ballast. And what I did here is I just linked this cell. This is the radius of the ballast. I linked that cell back over to the inertia calculator F17. So that's this tab right here, inertia calculator F17. So this is the outer diameter of the ballast. So as I change it here, it automatically updates it right here for this radius. I divide it by 2 to get the radius because that's the equations for our drag were in terms of the radius here. So so this already got updated now for the change in my drag due to that change in radius. Since we went from a washer that had a larger radius to a smaller radius, and so already I've got a reduction in my drag there just based off of that. Okay. So let's come back up here. So that was one of the easiest things we could do. Now let's go to something that's a little bit more tricky, but is something that is really powerful, and that is changing the aspect ratio of the main wing. Now we chose this main wing a little bit out of the blue. We just chose a semi-span. Actually, this should be 4.5, right? Yeah, we had a 4.5. There we go. That's correct. So 4.5 semi-span, 0.75 for the chord, and then that gave us an aspect ratio of 12. And I have these equations all linked. So this is telling me the area of the wing and the aspect ratio. And then we had this equation down here that was telling us the maximum aspect ratio that we could obtain based off of the stress inside of that inside of the foam here that we're using. So I'm going to pull up this equation here just so it's fresh on your mind. Remember, this is the aspect ratio. Our aspect ratio of the main wing has to be less than this equation, and that depends on the thickness of the airfoil, which this is in percentage, so that's a 0.12 for us. The maximum stress we can take depends on the weight of the wing. So as the weight of the wing increases, our aspect ratio actually can increase as well. But and then we're dividing here by some stuff that includes the wingspan. So as our so it's a function of wingspan and the weight that we're carrying at the fuselage. And here we're using for that fuselage the dowel plus the ballast weight. Okay, so that's what's going into the denominator here. So so it's kind of tricky to see into this thing too far because some of these things are linked. So for example, the weight of the wing and the wingspan are linked. As you change the wingspan, if we come back over here to our inertial calculator, if we change the wingspan, then the weight of the wing is also going to change. And so, is that a one-to-one relationship? It depends. So So it's a little bit tricky to see exactly what's going on here. So I'm just going to play with the numbers and see what happens. Well, already when I decrease the weight of the aircraft, or the fuselage and the ballast, the aspect ratio that's allowed went up from, I think it was about 40 before, now it jumped up to 92, right? Now this seems ridiculous, and it actually is. You're going to see that this doesn't stay there as we start to iterate on this. And that's because this equation is a bit complex. There's a lot of stuff built into this that's hard to look at individually, okay? So let's just, so I'm just going to leave that equation down here on the screen so we can refer back to it. But the next thing I did in my spreadsheet here is I said, let's leave the area of the main wing the same, okay? So I'm going to keep it at 6.75, so I don't have to reduce the area on the horizontal or vertical. I'm going to say that I'm going to keep my total area at 6.75. So I'm going to iterate on the main wing span here. I'm going to change the number there, and then I set this the wing chord up to give me. I typed in 6.75 here, and then I'm referencing that and the wingspan to tell me the chord, if I just stay with this Hershey bar rectangular wing, what's the chord that's going to continue to give me that area, okay? So as I change, so let me, for example, go up to a wingspan of 5, or this is a semi-span, by the way, then my chord would have to go to 0.675 in order to keep the same wing area, okay? And my aspect ratio just went up to almost 15. It was at 12 before. Okay, so that's our semi-span there, and what I want to do is increase that until I get to the maximum aspect ratio that I'm allowed to have, because that will obviously reduce the induced drag, right? We want to increase that aspect ratio. Okay, so the one thing though that this depends on that's not being updated as I do this is the weight of the main wing, and therefore the weight of the entire aircraft. Now, no, it's just the weight of the main wing that factors into this equation. So this main wing is over here in this inertial calculator. So I need to have the same number over here for the semi-span that I'm iterating on this, because this feeds into the weight. So I'm actually going to take this value here and set it equal to whatever I'm iterating on here. So when I update that semi-span there, it's going to update this semi-span here. And by the way, I already set the one, remember we had left and right broken out separately. I've set the one below it equal to the one above it, so that if I change this one above it, it changes the one below it. So I'm going to do that with the chord as well. So I'm going to, rather than typing this in, I'm going to set that equal to this chord right there. And now as I update this number here, so let's go back to 4.5. You can see that 4.5, this was the weight of the wing. And now when I go to 5, it changes the weight of the wing there, okay? Okay, and then this aspect ratio, again, this is linked. This is this equation here that's using all the information above it. And so this is the maximum aspect ratio that I'm allowed to have. Okay, so right now I'm at a wings or semi-span of 5, and so my aspect ratio is 15, and it's saying, oh, you can have a maximum aspect ratio of 75. Well, that's, what is that, 5 times greater, right? So let's put in a 25 here for that semi-span, and boy, that gives us an aspect ratio. Remember, my chord is linked to that. It's trying to keep the same amount of area. So actually, that wasn't, I couldn't just put in a 25 there to get an aspect ratio 5 times greater. I'm going to have to increment on that. So let me go back to 5, because by doing that, I got an aspect ratio of 370, which and my aspect ratio allowable here dropped to 3. So I'm going to go back to 5, and I'm just going to increment this up and see what happens. So as I increment up to 6, my aspect ratio went to 21 because we dropped the chord to keep the total area the same. And the aspect ratio allowed dropped to 52, okay? So let's go up to 7, see what happens. Now I'm at an aspect ratio of 29, and the aspect ratio allowed is 38. So you can see how complex it is. It's hard to see what's going on in here. But as I increase my wingspan here, my allowable aspect ratio is decreasing, and that's because it depends on all these other things that are also changing. So let's go up to 8 and see what happens. So at 8, I'm at an aspect ratio of 38 now, and now it's saying you can only have an aspect ratio of 30. So I'm going to have to drop that down. So let's try 7.5. Okay, 7.5, I'm at an aspect ratio of 33.3 with an allowable of 33.4. So that's about as close as we're going to be able to get to maximize our aspect ratio here. So let's just look at what that looks like on the actual glider. So that gives us a semi-span of 7.5. So put in 7.5 there, and a chord of 0.45. Okay, so that's saying that for the foam that we're using, that and the weight of the aircraft that we're carrying, that is that's the maximum aspect ratio I can basically have there. Okay, and that's if the main wing is carrying the weight of everything here on of the fuselage and the ballast. Okay, so that's that seems reasonable. I mean, that's a little, that's a pretty high aspect ratio. We're at 33. That's on the high end of gliders. Gliders can sometimes have aspect ratios up to that point. So, okay, so now we've optimized the aspect ratio, decreased the weight, and now let's just see what that does to our drag. Okay, so before, I'm going to come back over here. I have this performance spreadsheet, and this was based off of that original design. This was the weight of the aircraft, the wing area, the wingspan. And CD0, CD1, and CD2, those came from, I actually ran those, at 3 different angles of attack. So we ran our mock-up at 3 different angles of attack, added in the drag that was coming from this, from the ballast and the dowel, added that into the drag, and that gave me these 3 values here, CD0, 1, and 2. And from CD2, we can compute an Oswald efficiency. We were at around 70% before. And it said, well, your minimum drag airspeed is about 16, and your maximum L over D, you can look at L over D here, and we were getting up to somewhere around 25 as our maximum L over D. Okay, so let's see now what happens if we just update this information. I'm just going to run these at 3 different angles of attack. I'm going to fill in the lift coefficient and drag coefficient of this glider where I've changed this. Now again, I haven't set the horizontal to trim this out beautifully. I haven't set the vertical to do anything special. I just left those from what I had before. And right now I'm just trying to maximize L over D, and later I'll come back and I can tweak these things to for trim and stability and stuff like that. So anyway, let's just run an analysis here. We're going to run at angle of attack of -5. And first thing I want to check is that my reference area is the same, 6.75, so I've got the same amount of wing area. And we're getting a lift coefficient of 0.1851. Okay, and a drag coefficient of 0.0096. Now, what I want to do here is type in that 0.0096 and then add it to B74, which is whatever I'm getting from my ballast and dowel. So that's that number up there. Okay, then let's run this at 0 degrees angle of attack. And now I'm getting a 0.6984 and a drag coefficient of 0.0158. So that's going to be equal to 0.0158, and then I need to add on this drag delta there, and then at 5 degrees angle of attack, I'm getting 1.2183. Oh, I forgot to do one thing. It's not going to affect this really. Just a second, let me finish this. So this is 0.0345, and I need to say that that's equal to that plus the CD0 there, the change in drag due to the fuselage stuff. Okay, There we go. Okay, so what I forgot to do is to update my center of gravity location, because as I changed the main wing, my center of gravity also changed. So this is the new CG location, and so I should, technically I should have moved that around to match this CG location before I ran those, but it actually does not significantly affect these results, so I'm just going to not worry about it right now. Obviously for your glider you want to make sure you do that correctly. Okay, so what I have here plotted is lift and drag. So drag is a function of lift for these values here. So we can see, let's see. So this is drag as a function of lift, and these are then, this is the equation of the parabola then that goes through this data. And so for my new values here, and I'm just going to put them next to my old values here so I can compare them. I get a 0.0127, and then I get minus 0.00835 for CD1. So that's that number right there. And then the third one is 0.0231. 0231. Okay. All right, so I'm going to take these values now and just copy them, go over to my performance spreadsheet, and I'm going to paste them in here for these three values. And you see my Oswald efficiency, it said I went up to over 100%. Well, that's not true, because part of that is dependent on this stuff up here that I also need to update. So what's my total wingspan now? Let's come back over here to our main wing. It was 7.5, so my total wingspan is 15. The weight of my aircraft is at 0.641. So I'm going to 0.641. My wing area stayed the same. CL max I'm not going to worry about right now. The density didn't change. So again, it's calculated an aspect ratio of 33.3. That's correct. Wing loading is really low. And then these are my drag terms here. So it says that my Oswald efficiency went down to 41%. Wow. So, we might think, well, that was a bad idea to increase the wingspan or to increase the aspect ratio because my Oswald efficiency dropped. Well, the Oswald efficiency is a measure of how well you're doing relative to an elliptic wing. And because your aspect ratio is so high here, it actually doesn't help you a whole lot to go to an elliptic planform. The differences here, the differences to be gained by going to an elliptic planform become smaller and smaller at higher and higher aspect ratios. So anyway, that's kind of a topic for another day, but I guess I'm just saying don't worry that you have such a low Oswald efficiency factor here. This is also including the parasitic drag, which is now becoming more dominant instead of the induced drag. And so, comparing this to the performance of a perfect elliptic wing, we're going to get worse and worse as we go to higher aspect ratios. But that's okay. What we really came here to see is if our L over D had increased. And so, sure enough, if you plot L over D, and this is now, based off of this data here, this drag polar and this information about the aircraft, we're now getting an L over D of 38.5. So we went from 25 to 38. So that's a significant increase in distance that we can glide. In fact, let's just do the math right now. So equals 38.5 divided by, I think we were around 25 before. So we've gone up by 50%, right? We can glide about 54% further if we can get this thing to trim and be stable and everything else. We've increased the range of this thing by about 54%. So again, this is just some really low-hanging fruit for optimizing this glider. Of course, there are a whole lot more things that can be done here. We can play with the taper ratio of the main wing. We can play with actually trimming this aircraft with the horizontal tail. That can reduce the drag. We can increase the aspect ratio of the horizontal tail to do that. We can move it back. Anyway, there's a lot of things we can do. But these two things that I talked about, just moving the ballast and the increasing the aspect ratio of the main wing, are two of the most low-hanging fruit, most obvious things that you can do to this glider to increase its performance.